This is 4.1.1, Scalars and Vectors. First thing you need to be able to do is you need to be able to define scalar and a vector, because questions will ask you to define them. So a scalar is a quantity that only has magnitude. And a vector is a quantity that has both magnitude and direction. And a magnitude is the product of a number and a unit. This is quite important when you're talking about quantities that actually have units. Now sometimes they won't have units. If it doesn't have units, then just a number is fine to show a magnitude. But when a quantity has units, two different numbers can mean very, very different things. 6 meters per second versus 6 light years per second. Sorry, 6. Yeah, light years per second. Mean two different things. Yeah? Because although they both have the number 6 in them, 6 light years per second, which can't happen, is extremely fast. 6 light years per second basically means that something's moving faster than the speed of light, by the way, which can't happen. But hypothetically speaking, they both have the number 6 in them, but the unit that comes afterwards means very different things. So they have very different magnitudes, so the actual sizes are very different. So magnitude is the product of a number and a unit. Put a box around that. This basically means if it's the product of a number and a unit, product means to multiply. So let's start with something basics. A meter per second, that's a thing. So you have 6 meters per second, that means you have 6 lots of these things called meters per second. We start to use units as algebraic quantities, so we can manipulate them. So 6 meters per second, this is our number. This is our unit. And all that means is 6 times this thing that we call a meter per second. And the multiplication is called a product. Now, you need to be able to determine whether some things are scalars or whether they're vectors. You have to learn 2 special cases, and then the rest of them, just by using common sense, you're going to be able to figure out what they are. And to do that, you try one thing. You try to say upwards. So try saying upwards. And if you say that, you're basically giving something a direction. If the statement makes sense, you've got a vector. If the statement does not make sense, then you have a scalar. So if it makes sense, you have a vector. If not, then you have a scalar. So we can try two of them. So for example, 10 kilograms upwards. That doesn't make sense. What is 10 kilograms upwards? It's a property of the object. It doesn't have a direction. So that means that mass is a scalar. 10 newtons upwards. Well, that makes sense because we can draw force arrows upwards. Things can be pushed upwards. That makes sense. So therefore, force is a vector. We'll make a list of common scalars and vectors. And we'll start with special cases first. So we'll make two lists. So first one is displacement, measured in meters. So when we're talking about vector, we use the word displacement. When we talk about the non-vector version of displacement, in other words, I just give you the product, the magnitude, but I don't give you any information about direction, we then call it a distance. So this is a special case. Then you've got the velocity, which is a vector, measured in meters per second. And then the special case of that, if I give you its magnitude, but I don't give you any direction, no information on direction, we then call it a speed. In many calculations, these two, so displacement, distance, and velocity and speed can be interchanged in many calculations. But you always have to be careful if some initial information on directionality was given. Then we've got on this side acceleration, which is meters per second squared. And we've got force in newtons. On this side, we can put mass, measured in kilograms, and we can put density, measured in kilograms per meter cubed. Okay, start a new page. So let's imagine we throw a ball up, then catch it. The maximum height of ball is 1 meter. We imagine this process happening as if everything lived on a graph. So start with an arrow, so do a double-ended arrow. So at the top here, we've got positive displacement. And at the bottom, we've got negative displacement. In the middle, we've got start of the throw. So displacement here is 0. So with zero knowledge of any direction, the ball moved upwards by 1 meter, then it moved downwards by 1 meter, where it was caught from where it started. I'm going to repeat that statement without saying the directions. I'm going to stay quiet when it comes to directions. The ball moved by 1 meter, and then it moved by 1 meter. I got rid of all information about direction. So the distance there was 2 meters in total. So we'll do start. Then middle. End. So the distance is 2 meters, and the displacement, so it went up by 1 meter, so it had a positive delta, then it moved down by 1 meter, so it had a negative delta, so the total displacement is 0. It returned back to where it started from. Okay, next we'll do adding vectors. So you have to be able to do this in 1 and 2 dimensions. In rare cases, you might have to do 3 dimensions. But they'll be very rare, and once you've applied 2 dimensions, 3 dimensions becomes quite simple in the case for A level. So adding vectors in 1 dimension, you simply sum them up. You choose one direction as positive, one direction as negative. Again, we imagine things as living on a graph. A one-dimensional graph is just a number line. If you have a number line, well, if it's oriented horizontally, right is positive, left is negative. If you orient your number line vertically, up is positive, down is negative. So always use that as a rule. Everything lives on a graph. So in 1 dimension, simply add them up. In 2 dimensions, you end up with something called a resultant force. So in 2D, vectors give you a resultant. So we'll look at one example. If we had a box with 40 newtons upwards and 30 newtons to the right, that will resolve to one force that goes up in that direction with some angle theta. So it becomes the equivalent of a single force at some angle. So it's acting both horizontally and vertically. To find the magnitude, we use Pythagoras. So you can see that these make a right angle triangle if you put them together. When you're trying to make a triangle out of vectors, where one vector finishes is where your second vector begins. So I'm going to sketch this now. So I'm going to start with my 30 Newton horizontal. 30 newtons. And as I said, where one vector finishes, that's when you begin your second vector. So at the end of the arrowhead is where I'll start my second vector. That's my 40 newtons. And then to complete it with the resultant starts from the beginning of where you are drawing and ends at the end. So the beginning is at the start of my 30 newton arrowhead, of my arrow, and then finishes at the arrowhead of the 40 newtons. That's our resultant, F. And our angle, theta, from the horizontal. So, Pythagoras' theorem, F squared is equal to x squared plus y squared. And if you did it for this case, you get square root of 30 squared plus 40 squared is equal to F. And that just equals to 50 newtons. Then to get the angle, which gives you the direction, you're going to use trigonometry. So use trig for angle, theta. And if you've forgotten how to use trig, use so, ka, toa. My recommendation is always use the numbers that were given, if possible, and avoid using the numbers that you calculated for two reasons. Number one, oftentimes you're rounding the number that you calculated. And number two reason, what if you calculated it wrong? What if you typed it into your calculator wrong? That means that your angle is also going to be wrong. Right? It's very much possible that under pressure you type values into your calculator wrong. So therefore you got the force wrong, and then by extension using the wrong force you're also going to get your angle wrong as well. So in this case I'm going to use the opposite and the adjacent, so 40 over 30, and that corresponds to tan. So theta is equal to inverse tan, opposite over adjacent, which is 40 over 30. And that gives us 53 degrees. Okay, start a new page. Let's do an example. So we have a river. Our river is flowing at 4 meters per second. We have a swimmer who's trying to swim to the other side. He's swimming with a velocity of 2 meters per second. And the river has a width of 200 meters. Assuming no acceleration, velocity is equal to displacement over time. So v is velocity in meters per second. S is displacement in meters. T is time in seconds. So, part A. How long does it take the swimmer to cross? Part B. What is the resultant velocity on the swimmer? Part C. How far down the bank does the swimmer end up? And part D, what is the total distance traveled by the swimmer? You can pause the video here to attempt the question and press play when you're ready to see the solutions. Okay, so we look at the problem again. The river has a width of 200 meters. Our swimmer is swimming vertically upwards with a velocity of 2 meters per second. The river's also flowing at 4 meters per second. So our swimmer is going to be moving in a diagonal direction, so up and to the right. However, his vertical component remains unchanged. If we ignore the fact that he's also moving to the right at the same time, he's still moving towards the other side of the river at 2 meters per second. So in this case, you can ignore all horizontal directions and simply solve the time in terms of how long it takes for the swimmer to end up here, as if the river was not flowing. Because the time it takes for the swimmer to move to this point without the river flowing is the same amount of time it takes for the swimmer to end up here while the river is flowing. It takes the same amount of time. So let's solve that one. So the time is equal to the vertical distance or displacement over the vertical velocity, Vy. So we've got 200 over 2. That gives us 100 seconds. Part B, the resultant velocity of the swimmer. Well, the swimmer's moving towards the right by 4 meters per second, upwards by 2 meters per second. So let's draw that. So 4 meters per second and 2 meters per second. So his resultant velocity is v with some angle theta. So v is equal to the square root of 4 squared plus 2 squared. Which is the square root of 20. Which gives us 4.5 meters per second. And then if you needed to, you could work out the angle using trig. In this situation, we're not going to need to find the angle. Part C asks, how far down the bank does the swimmer end up? So all that's talking about is this horizontal displacement here. So for that, we only need the horizontal velocity. So Sx is equal to Vx multiplied by the time. Now again, as I said, the time it takes for him to move vertically upwards was the same time it took for him to move diagonally if the river was flowing. The same amount of time. So Sx is equal to Vx, which was 4, multiplied by 100 seconds. So he moves down by 400 meters. And then finally, the total distance traveled by the swimmer. So the swimmer moved horizontally by 400 meters and vertically by 200 meters. So the total distance he's moved is just a resultant of those. So S is equal to the square root of 400 squared plus 200 squared, and that equals to 450 meters.